Okay, so let's start with a brief recap of what was happening in the previous two lectures. Okay, so in the first lecture we discussed the classical Friedgut theorem. Okay, so we have a Boolean function from 0, 1 to the n to 0, 1, and we are given that it is close to degree 1, okay, with respect to some p-biased measure mu p, where we think of p as a constant, or anyway as bounded away from 0 and 1. Okay, and let's say that it is epsilon close to degree 1, in the sense that the L2 norm squared of the part of f beyond degree 1 has L2 squared norm at most epsilon. So this can only happen if f is order epsilon close to a Boolean degree 1 function, which is one of the following functions: a constant function or perhaps a dictator. Now we have a hidden constant here, and this hidden constant depends on p. And this dependence is necessary, and in fact, as p gets closer to 0 or 1, then this constant blows up. Okay, so in the proof we gave, this was because we did some normal approximation using the Berry-Essen theorem, and we considered the ratio between the third and second norms of the Fourier characters. Okay? And so the second norm is always 1 because that's how we construct them, and the third norm, it blows up as p gets closer to 0. Okay, so this is why the hidden constant, it blows up as p goes to 0. Now this is not because we didn't have the right proof, it's because, as we've seen last time, actually when p gets to 0, gets close to 0, then a different phenomenon happens. Okay, so then there are actually functions which are epsilon close to degree 1, but are not order epsilon close to any constant or dictator, and we have to modify the theorem. Okay, and the structure that we suggest instead is what is given by the biased FKN theorem. Okay, and here's a funny story, because I first proved the theorem for a different domain called the slice, and then I derived it in some way on the p-biased cube, but actually the right way would have been the opposite, of just proving it directly on the p-biased cube. These things happen. Okay, so now let me write the biased FKN theorem. Okay, so we're under the same assumption, only now the only thing we assume is that p is at most a half. Okay, if we don't assume that p is at most a half, then we have to replace everywhere p by p times 1 minus p. Okay, so in this case, the structure that emerges is that either f or its complement 1 minus f is order epsilon close to a maximum of m coordinates, okay, where m is at most the maximum between 1 and order square root epsilon over p. Okay, and we explained last time where this square root epsilon over p comes from. Okay, essentially, if we take the maximum of too many coordinates, then the function won't be close to degree 1. Okay, now there's a nice corollary, okay, that the function, under the same assumptions, the function is order square root epsilon close to a constant function or a dictator. Okay, and what this means is that if you're interested in understanding the structure of the function up to an error of order epsilon, then you need this more elaborate structure of a maximum of m variables, where m is at most the maximum between 1 and order square root epsilon over p. But if you're okay with losing a polynomial in epsilon, like getting only an approximation up to square root epsilon, then you recover the unbiased FKN theorem. Okay, and we'll see the same thing happening today also for the symmetric group. So it's up to you whether square root epsilon is good enough for you or not. Of course, square root epsilon, epsilon is the optimal approximation that one could hope for. Okay, so now a brief recap how we proved this theorem. Okay, so for every s, where s is going to be distributed according to mu 2p, that's a spoiler from last week. So for every s, we consider the restriction of f to 0, 1 to the s. Okay, and I'm going to explain in a minute how we obtain this restriction. Okay, so this restriction is some Boolean function from 0, 1 to the s to 0, 1, which on average is close to degree 1. It's actually absolutely close to degree 1. And now we apply the unbiased FKN theorem for p equal to a half and approximate the restriction of f to s by an honest to God constant or dictator function gs. Okay, this is just an application of the standard FKN theorem. And now we want to say that all of these gs functions, they really come from some global function. Okay, but first let me explain what I mean by the restriction of f to the coordinates in S. Okay, so there are kind of two ways to see it. Okay, so one way is I'm going to substitute 0 in all the coordinates outside of S. Okay, and in this way I can think of the result as a function that depends only on xi for I in S. The other way to think about it is I take the expansion of f as a polynomial in 0, 1, or the Fourier expansion. I guess you take the expansion as a polynomial in 0, 1, and you just remove all the monomials which mention some index not in S. Or conversely, you only retain the monomials which only mention indices in S. Okay, and this gives you a sum function which depends only on the variables xi for I in S. And this function is a restriction of f to S. Okay, it's exactly the same thing, so it's up to you which formulation you prefer. Okay, so this is how we define the restriction of f to the set S. Okay, and here I forgot to mention that p is at most a half, otherwise you have to replace p everywhere by p times 1 minus p, or the minimum between p and 1 minus p, which is the same up to a constant factor. Okay, so how are we going to paste these functions gs together? So we're going to identify gs with their coefficient vectors gamma s. Okay, so we write each gs as some constant plus sum of ci xi, where I is in S. And we look only at the coefficients, and we call this vector gamma s. Okay, so it's a mapping from 0 and S to 0 plus minus 1. And now what we do is we somehow paste them together, okay, into some global vector gamma. Now, why do we think that such a gamma exists? Because these gamma s, they come from the function gs, and these gs eventually come from f. So maybe that's why we should expect it, and we'll see in a moment. Okay, and finally, the last step in the proof that we saw yesterday was that we reinterpreted this vector gamma as a function g, and we showed that f is close to g. Okay, and in this way we also derived the bound on M by considering the way that gamma restricts to these vectors gamma s. Okay, and to that end, we used an agreement theorem, which is something we didn't have time to prove yesterday, and that's what we're going to start with today. Okay, so we're going to prove this agreement theorem or direct product testing theorem, which is what we use to paste the gamma s's together. Yeah, and here I'm reminding you that S in the proof, S is going to be chosen according to the distribution mu 2p. And then if you sample S according to mu 2p, and then you sample a random point x in 0, 1 to the S in an unbiased way, then this just gives you a sample from mu p. Okay, and this is why you think, why this has relevance, rather, to approximating f with respect to the p bias measure. Okay, so the way that we paste the gamma s together is we look at what happens when we sample two correlated or coupled copies of mu 2p. Okay, and I'm going to start by specifying this distribution. And then we're going to say that if you sample S1 and S2 according to this distribution, then these gamma S1 and gamma S2 typically agree, and this is why you think that you should be able to paste them together to some global gamma. Okay, so how do we sample S1 and S2? So you go over all the elements I and n independently. You put I in both S1 and S2 with probability square root 2p, where square root 2 you can really replace it by any number which is strictly between 1 and 2. Now you put I only in one of these sets, so only in S1 or only in S2, with probability 2 minus square root 2 of p. Okay, so this is just in S1, not in S2, and this is not in S1 and just in S2. And with the remaining probability, you don't put it in any of the sets. And what we need is that this probability that I'm writing here is non-negative. And this will be the case when p is smaller than some constant. Now, I claim the theorem for all p at most a half, but if p is between a half and this constant, then it just follows from the unbiased FKN theorem. Okay, so in a moment we're going to see what the agreement theorem looks like. Yeah, and maybe it should be observed that if you look just at S1 or just at S2, so you look at the marginal distribution of only one of the sets, then you get exactly mu 2p. And this is sort of why we needed square root 2 to be between 1 and 2. Okay, so now let me state the agreement theorem. Okay, so we sample S1 and S2 according to this coupled distribution. And we assume that the gamma S1 and gamma S2 typically agree. In the following sense, if you sample S1 and S2 according to this distribution, and you look at gamma S1 and gamma S2, then they typically agree on the intersection. Okay, so what this means is that gamma S1 at 0 equals gamma S2 at 0. And also, for every index which is in both S1 and S2, then gamma S1 at I is equal to gamma S2 at I. Okay, and this should happen with probability 1 minus order epsilon, or equivalently the probability that they disagree is order epsilon. And what the agreement theorem claims is that if you make this assumption, then there exists some global function gamma, okay, global vector gamma, such that with probability, except with probability order epsilon, if you choose S according to mu 2p and you restrict gamma to S, then you get gamma S. Okay, so this is the statement of the agreement theorem. And let me remind you that gamma S was not only a function from 0 using S to some alphabet sigma, but also it is a junta. Okay? In our case, it's even a one junta. And what this means is that sigma contains special symbol 0, and the support of gamma S has size order 1. Like I said, in our application, the size of the support is 1, but the theorem will still be true even for any other size of the support. Now I should say that actually the agreement theorem holds even without the junta assumption. Okay, and this was proved by Dinur and Steurer. But I never managed to understand their proof. Okay, their proof is rather tricky. But in case that you can assume that these gamma S's are juntas, then the proof becomes a lot easier and I think quite intuitive. Okay, so this is the proof that we are going to give. Now there's a nice story here. So these agreement theorems came up for me as part of my work, which I'm going to present tomorrow. Okay, and it all started where Edith was saying that her students proved some kind of generalization of this agreement theorem, which would have been useful for our application. And then it turned out that actually the students didn't manage to prove it, so we worked hard and we did manage to prove it eventually. And then it turned out that we really only needed this junta agreement theorem, which is a lot easier. But this was only a few years later. Okay, so these things happen. Okay, and now let me remind you why in our particular application it is the case that gamma S1 and gamma S2 agree. Okay, so it is the case that GS1 and GS2 typically agree on their intersection. Okay, and why is this the case? This is because both of them are on average close to the same function f. Okay, so if you take f and restrict it first to S1 and then to the intersection of S1 and S2, or you restrict f first to S2 and then to the intersection of S1 and S2, then it amounts really to the same thing. Okay, and because this f is exactly the same, then these g's are close to one another. Now you have to somehow go between this closeness of g and the closeness of gamma. And why is this the case? Because these functions g, they depend on at most one coordinate. So the difference depends on at most two coordinates. And moreover, these functions are integer valued. So either they are equal exactly, or otherwise they differ with constant probability, and the difference can be bounded below by 1. Okay, so if gamma S1 and gamma S2 disagree, then the distance between GS and GS2 on their intersection squared is omega 1. Okay, and that's why we can convert this order epsilon bound on the g's to an order epsilon bound on the gammas. Now for this to work, we need to compute the distance between the g's with respect to the correct norm, which is in this case mu of 1 over square root 2. Okay? So this is why it's important that square root 2 is strictly larger than 1. Okay, if for example we just sampled S1 and S2 independently, and then this would have been useless because we wouldn't have been able to relate the distance in g's and the distance in gamma. And this is because instead of 1 over square root 2, we would have had to put there somewhere else, something else, and then the relation wouldn't have been order 1. Okay, so just try it out and see why it doesn't work. Okay, but really, in short, what happens here is that, rather the fact that we're using is that every two juntas, they're either identically the same or they differ with constant probability. Okay, so the juntas, they form a code. And this is what was needed to convert between distance in g's to distance in f. Okay, it's really a crucial part of the proof. Okay, and now in a moment I will explain, it's not so mysterious, how we construct this global function gamma. Okay, so there's nothing mysterious about it, and in fact it's quite natural. So it's coming up very shortly. Okay, so in only a few moments. Okay, so now I'm ready to explain how we construct this global function gamma. Okay, so we start with gamma at 0. Okay, so gamma at 0 is going to be the most common value of gamma s of 0. Okay, so I'm looking at all the possible values. In this case it's just 0 and 1, but this works for every alphabet. And I'm choosing the one which is most popular, which appears with a higher probability when s is sampled according to mu 2p. Okay, in gamma I, it's very similar. It's going to be the most common value of gamma s of I, but here we take mu 2p restricted to sets S which contain I. Okay, so we call this majority decoding, even though it's really plurality decoding. And this actually implies the sparsity of the vector gamma. Okay, so this is something I didn't say explicitly, but it is the case. So this corresponds to the bounding on M, which is order 1 over p. Okay, and now let's see the proof, and we're going to start with the proof for gamma of 0. Okay, so what we want to show is that if we choose S at random according to mu 2p, then except for probability order epsilon, gamma S of 0 is going to equal to gamma of 0. Okay, and really the point here is that we can compare this to what happens if we sample two sets S1 and S2 at random. And instead of comparing gamma S of 0 to gamma of 0, we compare gamma S1 of 0 to gamma S2 of 0. Okay, so what's the idea here? So gamma of 0 is the most popular value. So this is the value which is least probable that gamma S will be different from gamma S of 0. Okay? So to prove this inequality, then you first sample S2 and you look at gamma S2 of 0 and you say, okay, so the probability that gamma S1 of 0 is different from this value is at least the probability that gamma S1 of 0 is different from the most popular value of gamma S of 0. Okay, so this is how we relate the probability that we're interested in to something that at the very least involves two functions which are sampled independently. Okay, so this is maybe a bit confusing, but if you write it out, then you see that it's true. Okay, and now we have to somehow relate this probability here to the probability of agreement, which is what we are actually being given. Okay, so we're going to see in a bit how to do it. Okay, so what we would like to show is that this is can be bounded by the probability that if we sample S1 and S2 in a coupled way, okay, according to this coupling on the left, then gamma S1 of 0 is different from gamma S2 of 0. Okay, so this inequality here, it's really about expansion, okay? So we can think of this coupling between S1 and S2 of kind of random walk. Okay, and I'm going to explain in a bit how. And now if this random walk is not mixing, okay, then what could happen is we could have these two big blobs of zeros and ones, and maybe our random walk will stay inside the blob. Okay, in that case, this inequality will be wrong. But if the random walk is mixing, is an expander, has the right eigenvalue, whatever, then this inequality will be true. Okay, now what is the random walk here? So I gave you a way to sample S1 and S2 in a coupled way. Now let's say that you are at state S1, okay, so you fix S1, and you sample S2 conditioned on the value S1 of S1. Okay, so this gives you a kind of random walk. And we want to show that this random walk is mixing. This is essentially equivalent to what is written here. Okay, so this inequality that is written here is really equivalent to a spectral gap. Okay, now there are several ways of showing it. Okay, so we know the eigenvectors in this case. Okay, they're just the 2p biased eigenvectors, and we can just calculate the eigenvalues. Okay, it's no big fun, but it's also not very difficult, and this calculation just gives you what you need. But there are also other options which are arguably cleaner. Okay, so you can use some sort of coupling to directly argue this inequality, and you can see this worked out in the notes. Okay, so if you're curious, then look it up. Okay, so this was about how do you paste gamma at 0, and now we're going to move on, after I erase the board, to how we paste the remaining coordinates. Okay, so I mean, we've seen the definition of gamma I, but let's see why this works. And here there will be a trick, okay, something which only works in the case of juntas and is a lot more difficult in the general case. Okay, so we'll see it in really just a moment. Okay. So we basically want to do the same thing that we did for 0, but now for the rest of these coefficient vectors. Okay, so we just repeat what we did in the case of zeros. So let's first state what we want to show. Okay, so what we want to show is this probability when we sample S1 and S2, when we sample just S according to mu2p, that gamma S of I is different from gamma of I for some I in S. So we want this probability to be small, to be order epsilon. Okay, and how are we going to show this? We're going to use the union bound. Okay, so this probability is at most a probability, the sum over I rather, of the probability that gamma S of I is different from gamma of I, and this is assuming that I is in S. Okay, so instead of taking a sum just over the I in S, we're going to take a sum over all possible I, and we're going to sum over the probability that I is in S and gamma S of I is different from gamma of I. Okay, and it's maybe a bit confusing whether this is really correct, so we had a small discussion, but it seems that this is correct. Okay, and formally you can see it by using conditioning and unconditioning, and this way you don't get confused. And this is worked out in a bit more detail in the notes. And now we do exactly the same thing. We apply expansion in exactly the same way. And okay, we have to, we're skipping a few lines to save time, but it's really, you'll have to trust me that what you get if you do this is you show that you can estimate the sum with the expectation over S1 and S2 sampled in a coupled way of the number of indices in S1 intersect S2 on which gamma S1 and gamma S2 differ. Okay, so this sum is still there. Now it's hidden in this number of indices. Okay, and now crucially we're going to use the junta assumption. Okay, so because both gamma S1 and gamma S2 are juntas, then they can only differ in a constant number of coordinates. If each of them depends on its most m coordinates, then the number of differences is at most 2m, which we think of as constant. In our case, it's just 2 coordinates. Okay, so then the number of coordinates where they differ and whether they differ at all it's really the same thing. Okay, up to this constant of 2m. So we can bound this by the probability that gamma S1 and gamma S2 disagree. When S1 and S2 are sampled in a coupled way. And this is something that we know happens with small probability. Okay, so this is the trick. If you do not assume that the gamma S's are juntas, then this doesn't work because it could be that sometimes the number of disagreements is very large. And maybe there's some sort of conspiracy and the number of disagreements is either 0 or very large. And in this case, this argument wouldn't work, and then you need to do what Dinu and Steurer do, which really, although I was able to verify the proof line by line, I never really intuitively understood what is going on. Okay, so if you're interested in understanding this proof intuitively, then I think people like Domin are able to somehow understand it. Okay, but in our case, everything is a junta, so we don't need to try so hard, and we have this very slick and simple proof. Okay, so instead of a few pages of inscrutable calculations in our paper for the generalization of this theorem, then this entire proof fits in like 1 or 2 pages. Okay, and for me, having a short and intuitive proof is sometimes better than having the proof of a more general result. Okay, I guess it's just a matter of taste. Okay, so you let me know which ones you prefer. Okay, and now we're going to move on to a different domain, the symmetric group. And we're going to ask 2 questions. First question is, what are the Boolean degree 1 functions on the symmetric group, which is the group of all permutations of the numbers 1 to n? Okay, and I'm going to define to you in a second what does it mean for a function on the symmetric group to have degree 1. And the second question that we're going to ask is the analog of the FKN theorem. Okay, so what can we say about Boolean functions which are close to degree 1? And what does it mean for a function to be close to degree 1? It means that it's close to some degree 1 function. Okay, and we're always going to consider the uniform distribution over the symmetric group. People sometimes consider other distributions, such as the Mellows distribution, but we will only be considering the uniform distribution here. Okay, so what does it mean to have degree 1? So we think of the symmetric group as the collection of all n by n permutation matrices. Okay, so we can think of the input as n squared variables, xij, which are 0, 1, and they are promised to form a permutation matrix. So each row and each column contains a unique 1. Okay, and this gives us a notion of degree that I'm going to define in a second. Yeah, this is something which is very natural, I think. So what is the degree of a function? So you can express your every function as some polynomial in the xij's. And we define the degree of the function as the smallest degree of a polynomial which represents the function. That is, it agrees with the function on all permutation matrix inputs. Okay, so in contrast to the case of the Boolean cube, here there is more than one representation. Okay? So one reason is that the sum of each row is 1 and the sum of each column is 1. Okay, and this allows us to create many representations of the same function. For example, because the sum of each row minus 1 is 0, then we can get many representations of the 0 function by taking multiples of the sum of any row minus 1, or the sum of any column minus 1. And actually, the ideal generated by these identities, it leads to all the functions which are identically 0 on the symmetric group. Okay? Now there's a different way to define degree using some sort of canonical representation, which is some sort of Fourier expansion of functions on the symmetric group. Okay? So every function in the symmetric group has a unique representation as a multilinear polynomial with the following properties. So multilinear, and just to remind you, there's no variable that appears squared. So first we ask for no monomial to be identically 0. So as an example, we don't want any monomial to contain both x11 and x12, because on every permutation, one of them will be 0. Next, we have these funny conditions on the derivatives. So if we take our polynomial, okay, and we sum all the derivatives on one of the rows, or all the derivatives on one of the columns, then we have to get the 0 polynomial. Okay, it's kind of a strange condition, but it turns out that this is what you need to get a canonical representation. Okay, and you might wonder whether polynomials that satisfy these funny conditions even exist. Okay, so before I give an example, let me just say that the degree of this unique representation is also the degree of the function. Okay, so this is another way to define degree. And here's an example of a polynomial which satisfies these conditions. So it's x11 minus x12 minus x21 plus x22. And you can also multiply such polynomials. Now, how do you get this polynomial? You take the determinant of x11, x12, x21, x22, and you sum over all the first order partial derivatives. Okay, it's a very strange construction. And it turns out that if you do the same for higher derivatives, then it still works. You still get polynomials which satisfy these conditions. And taking products of such derivatives and then summing over them, this gives you all possible polynomials which satisfy these funny conditions. Okay, so if you're interested in this, then talk to me. I'm just stating this, so in case it piques your interest, then you come talk to me. Okay, now there is yet another equivalent way to define degree, and this is using representation theory. Okay? So representation theory gives us a decomposition of the Laplacian of the symmetric group. So let's say you take the transposition graph. So you connect any two permutations which differ by transposition, and you can consider the Laplacian. And now you look at the eigenspaces of the Laplacian. So the eigenspaces, they turn out to be indexed by partitions of n. Okay? And we imagine that these each of these partitions, they are arranged from the biggest part to the smallest part. And the degree of a partition is the sum of the parts beyond the first part. Or said differently, a partition has degree d if the first part is n minus d. And now you can define the degree of a function to be the largest d for which the function has some component on a degree d eigenspace. And it turns out that this gives you exactly the same notion of degree as what you get from these polynomials. Okay, so we think of this representation theoretic definition as a spectral definition of degree. And these definitions using polynomials, we think of them as spatial definitions of degree, spatial from space. And it turns out that all of these three definitions, they coincide. Okay, and this suggests that this notion of degree is the right notion of degree. Okay, so Guy commented that this actually works in all Lie groups. Okay, you can define degree in this way, and these two notions of degrees will coincide. And I mentioned that sometimes you have a reason to define a slightly different notion of degree, where you compare both the partition and the conjugate partition. Okay, but I won't say too much about this because this is taking us too far afield. Okay, so now we're going to turn to answer the questions that we stated, starting with question 1. Okay, so question 1 was answered by David Ellis, Ehud Friedgut, and Haran Pilpel. Okay, so here I should comment that Pilpel is kind of a funny name because in Hebrew it means pepper. And here's what they showed. So they showed that Boolean degree 1 functions are dictators. Of course, before I tell you what dictators are, then I haven't told you anything, okay? So they just define dictators to be the characterization of Boolean degree 1 functions. But this is quite suggestive, as you'll see from their description. Okay, so they come in two types. The first type, for some index I in n, and for some subset j of n, the function is as follows. It's the sum over all j in capital J of xij. Okay, so this is one form. The other form is just the dual. So for some index j in n, and for some subset I of n, f is the sum, where this time we sum over indices in I, in capital I, the sum of small I in capital I of xij. Okay. So maybe it's not completely clear what this means, so let me restate it in terms of the input permutation itself, pi. So functions of the first kind, they really depend only on pi of I. So pi of I dictates the answer. And the answer is 1 if pi of I is in J. And similarly, in the second case, what dictates the answer is pi inverse of J. Okay, the answer is 1 if pi inverse of J is in I. And here we see the symmetry that is inherent in the symmetric group, where we cannot distinguish the symmetric group from what happens when we invert all the permutations. Okay, which corresponds to the transposition of the input permutation matrix. Okay, and this kind of symmetry makes some of the proofs harder, because you don't know if you're aiming at functions of the first kind or at functions of the second kind. Okay? And now let me tell you how to prove this. So this is not quite how they proved it, but it's an equivalent proof. Okay, so let's suppose that f is the Boolean degree 1 function. We will consider the Birkhoff polytope, which is the convex hull of all permutation matrix. Okay, in other words, it's the polytope whose vertices are the n by n permutation matrices. And it's known, Birkhoff proved, that this polytope consists of all the doubly stochastic matrices. Okay, so this is just a different description of the polytope, or sometimes we think of it the other way around. the vertices of the polytope consisting of doubly stochastic matrices are the permutation matrices. And now we're going to look at f inverse of 0. Okay, and this is because f is a linear function, then f attains its minimum over the entire polytope at a vertex, so its minimal value is 0. Let's assume it's not the constant 1. Okay, so f minus 1 of 0 is a face of the polytope, so it must be contained in a facet of the polytope. And what are the facets of the polytope? So we know that all the facets of the polytope are xij equal to 0. Now what does this mean? So if xij is equal to 1, then we cannot be in f inverse of 0. So f must be equal to 1. So now if we subtract xij, then we still get a Boolean degree 1 function. Yeah, so obviously the function is still degree 1. And again, why is it Boolean? Because if xij is 1, then necessarily f of x is 1. And then f of x minus xij is 0. Okay, and this crucially relies on the fact that we know the facets of this polytope P. This is given to us by this classical theorem of Beekhoff. Okay, and now what do? We just iterate. So we remove xij, and if the remaining function is not 0, then we remove another xij, and another, and eventually we will be able to do what? To express f as a sum of xij's. Okay, so we just do it inductively, and each time the number of ones in f decreases, and therefore we will eventually get to the 0 function. Okay, so the end result is that f can be written as a sum of xij's. Now, because f is a Boolean function, then what can we say about these xij's? We cannot have two xij's which are not either on the same row or on the same column, because then the sum would not be Boolean. The sum would be at least 2. Okay, so any two xij's in the sum are either on the same row or in the same column, and this readily implies that in fact all of the xij's in this sum are on the same row, or all of them are on the same column. So, in other words, f is a dictator. Okay, and this concludes the proof. Okay, now let me now make two simple remarks. So one of them is that the original proof of Alice, Friedgut, and people was not really framed like this. It was framed in terms of LP duality. Okay, and this point of view is an idea of Nathan Lindsay. But really it's the same thing. Okay, so it's just a different way of looking at things. Now second, if we have any other situation where we know the corresponding facets of the polytope, then we can similarly characterize all the Boolean degree 1 functions. And one example is the perfect matching polytope, okay, which is a collection of all perfect matchings in Kn. So this is sort of the non-bipartite analog of the permutation group, of the symmetric group, which is the collection of all perfect matchings in the bipartite graph Knn. Okay, so in the case of the perfect matching scheme, the polytope is a bit more complicated. And indeed, also the collection of all Boolean degree 1 functions is slightly more complicated. So we also have, we can take the edges of a triangle and sum over them. This will also be a Boolean function, and also the complement of this. Okay, and you can essentially read this off from the description of the perfect matching polytope. Okay, so this is all I have to say about question 1. And now, after I erase the board, I will move on to question 2. Also, while erasing the board, let me just mention that what Alice, Friedgut, and people actually showed, and what this proof actually gives, is that if you have a non-negative function f, which is degree 1, then you can write it as a non-negative combination of the xij's. Okay, so this is essentially the same proof. It's a nice exercise. This is a stronger property. Okay, so now let's move on to the second question. Okay, which is the analog of the FKN theorem for the symmetric group. Okay, so suppose we're given a function, a Boolean function f on the symmetric group, and this function is close to degree 1. Okay, which again, it means that it's close to some degree 1 function, and we even know how to get this degree 1 function. Let's say starting at the canonical representation, we just remove everything beyond degree 1. Okay, so what can we say about such functions? And we expect a result which is similar to the biased FKN theorem, okay, with the value of p which is 1 over n. And why is that? Because the probability that each individual xij is equal to 1 is exactly 1 over n. Okay, and this is also exactly how the FKN theorem for the symmetric group is going to look like, although maybe it's somewhat less obvious than the case of the biased cube. Okay, so we can show that either f or its complement 1 minus f is close, order epsilon close, to, again, a maximum of some collection S of xij's. Okay, and I'm going to give you a condition that S has to satisfy. Okay, so first, S contains order n many xij's. And second, this is a crucial condition, the number of pairs of xij's, which are neither on the same row or in the same column, we're going to see a picture in a bit, is order of epsilon n squared. And I'll let you think, and why epsilon n squared? Okay, this is somewhere related to the square root epsilon over p, which we saw earlier. Okay, and moreover, if we take a maximum of such a set of xij's which satisfies these conditions, then the resulting function is order epsilon close to degree 1. Okay, and this means that our structure is in some sense optimal. As a corollary, f is order of square root epsilon close to a Boolean dictator. Okay, and this is exactly the same as what happened in the case of the biased cube. Okay, so if you want to understand the structure up to only square root epsilon, then you just get a dictator, you don't get anything new, you just get a Boolean degree 1 function. But if for some reason you want to know the structure up to a smaller error of only order epsilon, then you get this more interesting kind of structure, which is it's a maximum of a set of xij's which are, roughly speaking, on the same row and column, but with some sort of mistakes. Okay, like maybe not the first thing you would think, but this is really the structure you get. And this conversely clause shows this optimal. Okay, now why do we expect there to have only few pairs which are not in the same row or column? So just as I drew here, because in this case there's a chance of 1 over n squared for these two xij's to be 1, and then the function is not Boolean. Okay, now if you take a union bound, then you get that you expect the number of such pairs to be order of epsilon n squared. Now it turns out that this union bound is tight, and this is essentially because the size of S is order n. Okay, so we can reverse the union bound because the set S is small. Okay, I'm going to say more about this tomorrow when we discuss the degree D extension of the biased FKN theorem. Okay, so now let me briefly hand-wavy explain how the corollary follows from the theorem. Okay, so there are essentially two cases. Okay, one case is where all these xij's are all over the place, and in this case there cannot be too many of them because otherwise there would be too many of these pairs, and this implies that the function f is close to constant. If they're not all over the place, then there is some row or column which contains a significant number of them, and then each other xij which is outside this row or column will contribute many of these pairs. So there cannot be too many of them, and this is why this significant row or column is actually a good approximation for the entire function f. Okay, so this is roughly speaking how this corollary is proved. And this square root epsilon is tight, and here's the tightness example. So your set S is going to correspond, it's going to contain xij's in two rows and roughly square root epsilon columns. Okay, so square root epsilon n columns, sorry. So you can check that the number of bad pairs is like epsilon n squared, but in order to get a dictator, you have to remove square root epsilon n xij's. Okay, so this shows that the corollary is tight. Okay, and now I'll describe how, very briefly, how this theorem is proved. Okay, so this theorem is proved using exactly the same approach as we've seen before in the case of the biased cube, by reduction to the unbiased cube. Okay, but maybe it's not so clear what is the relation between the Boolean cube and the symmetric group. Yeah, how do I find a copy of the Boolean cube inside the symmetric group? Right, it's not so obvious. So let me tell you how to do it. So we sample two permutations in Sn, alpha and beta, and now we consider the following set of permutations. Okay, this is going to be our copy of the Boolean cube. So we look at all the permutations which map the set alpha 1, alpha 2 into the set beta 1, beta 2. Okay, there are two ways to do it. And also they map alpha 3, alpha 4 to beta 3, beta 4. Okay, and so on. Okay, so we have like n over 2 of these conditions. And this gives us a copy of the n over 2 dimensional Boolean cube. Okay, and if we choose a random copy of this form, by choosing alpha and beta at random and a random point, it gives us a random permutation. And now we can let the variable y1 control how do we map alpha 1, alpha 2 to beta 1, beta 2, and let y2 control how do we map alpha 3, alpha 4 to beta 3, beta 4, and so on. Okay? And all that remains to check in order for the general framework to work is that if we start with a degree 1 function on the symmetric group, then this gives us a degree 1 function on the Boolean cube, on the random copy of the Boolean cube. Okay, so let's say that f, it's actually not f, it's the low degree part of f at most 1. Let's say that this is a degree 1 function. Okay, and indeed f at most 1 is a degree 1 function. And let's take some representation of it. It's not unique, but some representation, some Cij, xij. And let's see what happens when we restrict to the cube. Okay, so if we restrict to the cube, then what we get is the sum of many terms. So let's see the contribution of the first line. So we get C alpha 1 beta 1 plus C alpha 2 beta 2, now plus Y1 times C alpha 1 beta 2 plus C alpha 2 beta 1 minus C alpha 1 beta 1 minus C alpha 2 beta 2. Okay, I mean, this is something which is easy to check, and I'm just writing it in full. Okay, and you take the sum of all n over 2 terms of this form. So this is the restriction of f at most 1 to this copy of the Boolean cube, and you can see that this is degree 1. Okay, so now what we do is we apply the FKN theorem, and we approximate this new function by a constant function or a dictator. And now we have to somehow take all of these pieces and paste them together. Okay, so in the original paper we don't use an agreement theorem. There's some kind of shortcut, which is actually what also happened in the original proof of the p-biased FKN theorem. But Noam Lifshitz found a way to prove an agreement theorem. Okay, so the way that we couple two copies of these random copies of the Boolean cube is we take one of these copies and then we choose at random half of these pairs and we disperse them. So like we break them apart. So instead of looking at all permutations that take alpha 1, alpha 2 to beta 1, beta 2, then we, in a random way, we say no, we look at all permutations which actually map alpha of 1 to beta of 1 and alpha 2 to beta of 2. Okay, so in this way we go down to a lower dimensional cube, and in the same way we can go up to a higher dimensional cube. Okay, so we go down and then up, and this gives us a kind of correlated copy of the Boolean cube. Okay, and if we can prove an agreement theorem for this type of random walk, which is indeed possible, so this is what I worked on with Noam Lifshitz during the previous week, then you can paste these coefficients together and eventually prove the theorem. So I haven't yet found the best way of doing this, but once I do, I will let all of you know. Okay, so now there was an interesting question from the crowd. How general is this approach? Okay, so is there some kind of abstract framework with which captures this kind of argument? Now, I don't have a complete answer for this, but I can say a few things. So first of all, this approach also works for the so-called slice. So when we fix the number of ones exactly rather than varying it binomially. And it also works for something called high-dimensional expanders. But more generally, some of this theory, which becomes more interesting when you look at degree D functions, it works in this simplicial context. Okay, so for some of these domains, like the Boolean cube and the symmetric group, you can think of them as simplicial complexes. In the case of the symmetric group, for example, the facets of your simplicial complexes are going to be the permutations in the following form. Okay, so it's going to be the set of pairs 1 pi of 1, 2 pi of 2, 3 pi of 3, and so on, up to n pi of n. Okay, so this is an n-dimensional complex. And you can consider restrictions of this facets to smaller dimensional faces. This gives you partial permutations, and they help you in understanding what is going on. You can do the same on the Boolean cube. So now the way that you encode a point x is as a list of pairs 1x1, 2x2, 3x3, and so on. Okay, so these are your facets, and if you have just a sort of a partial point, then this gives you a face. Okay, and now we have a few axioms, and assuming that your complex satisfies these axioms, then you can carry out what we're going to see tomorrow. You can carry out the classification of Boolean degree D functions. Okay, and it's possible that in the same way, if you can define a kind of random walk operator for which you can prove an agreement theorem, then you will somehow be able to deduce a generic FKN theorem. Okay, and I think this is quite an interesting direction that I hope to pursue. Now, some of the domains that we're interested in and that I'm actually going to discuss tomorrow, they don't correspond to simplicial complexes, but to other kinds of complexes. Okay? As an example, you can consider the Grassmann scheme, which I'm also going to consider tomorrow. Okay, so this is the collection of all k-dimensional subsets of an n-dimensional vector space over some finite field. Okay, so you take some finite field FQ and an n-dimensional vector space over it, and you look at the collection of all k-dimensional subspaces. Okay, now you can define degree in the same way, where now your variables are whether the subspace contains a certain vector or a certain degree 1 subspace, it's equivalent. And now you can ask which functions are degree 1 and which functions are close to degree 1, Boolean functions I mean. So we'll see the answer to the first question tomorrow, but the answer to the second question is unknown. And one reason is because we can't use this restriction business, because if you start with a degree 1 function and you restrict to a copy of the Boolean cube, and these can be constructed, then you no longer get a degree 1 function. And this is because the complex corresponding to the Grassmann scheme, the Grassmann complex, is not simplicial. Okay, so the faces are subspaces rather than just sets. So they grow in a different way. They belong to a different lattice, to the subspace lattice. Okay, so this approach might work in the simplicial case.